All right, so yesterday at the end of class, we were talking about scalar versus vector quantities, okay? And I reminded you that you've probably all seen Despicable Me at some point. Remember Vector, the supervillain, whose crimes all have magnitude and direction, okay? So all vector quantities have magnitude and direction. There's a measured value with units, okay, and then there's a direction. That direction in Science 10 is, well, we only do what we call one-dimensional vectors in Science 10. So forward and backward, right and left, north and south. You're never going to have to do any trig, okay, in Science 10 for vectors. Okay? First thing we do in Physics 20 is two-dimensional vectors, where I could have a vector that's 10 degrees east of north. Okay, and then, okay, I've got a triangle and I have to find sides and stuff like that. We don't do that in Science 10. We just have to keep track of forward and backward. Okay, positive and negative is as complex as we get. So what we're going to look at today is how we look at things society-wise and how wrong that is, okay? Or how different from physics that actually is. So I'm going to ask you this question. How far is it to Edmonton? Okay, that's always the answer I get. It is not the answer to the question. You just told me how long it takes to get to Edmonton. What did I ask you? Right. Here's one of our societal problems, okay? And it's worldwide, okay? When someone asks, how far is something? We tell them how long it takes to get there. What's really wrong with that?
It doesn't give the actual distance.
Well, it doesn't give the actual distance. It's probably, because of how society works, what they wanted, okay? When we ask how far away is something, we generally do want to know how long it takes to get there. It's just a messed up way we ask things, okay, in our culture. But the problem with time is it's dependent on two other things. It's dependent on how far it actually is, which is what I asked, and how fast you can go. Guys, I have driven to Edmonton and back, I can't tell you how many times. Okay? And it has never taken the same amount of time twice. Okay? I have come back from Edmonton in 9 hours. I've gotten to Edmonton in 2 hours and 38 minutes. My friend was crazy. Okay? Right? Like he drove really fast and somehow did not get pulled over, okay, all the way there. So, yeah, and then they had to like peel my hands off the holy crap bar. So, yeah, it takes a different amount of time depending on how fast you go and what route you take. Is there a bunch of different ways to get to Edmonton?
Yeah.
Yeah, but I mean, we usually just go straight up to QE2 and we're there, okay? But that time isn't an accurate value. You don't know that it's going to take that long unless you know the two other values, okay? So it's something we have to get our minds around. When a question asks you how far something is, it wants an answer in
Kilometers.
or meters, yeah. I mean, we usually use meters, but sometimes we use kilometers. Okay, so we definitely need to understand that the way we talk about things in our society is not accurate from a physics perspective. Okay, and it's not just North American culture. Europe does the same thing. Okay, like when you ask somebody, well, how far is it, from Rome to Milan? And they're like, that's about 4 hours. Really? Like, I asked how far. Okay, but now there, it's a little different. Do they drive as much in Europe? Now, what do they take a lot more often? Train. Trains aren't susceptible to traffic in the same way that cars are. Okay, so a train is a lot more reliable in terms of how long does it take to take the train from here to here. Well, that's probably a more reliable time number, okay, than it is on the road where there could be construction or whatever. Okay, so we have to watch out for that because doing that can really get us in trouble. Okay, I'm going to tell you kind of an embarrassing story that happened to me. Okay, a buddy and I years ago, probably before you were born, that's not the embarrassing part, we're doing a backpacking trip through Kootenay National Park. And we had this exceptionally long day where we went from like Flow Lake up to, I can't remember what the pass was called, and then down, and then we had to go back up to Tumbling Pass, and then down to Tumbling Creek Campground. And it's like a 34-kilometer day, okay? 2 passes, and it was end of July. We'd run out of water, and you need water to hydrate your food, so we were kind of cooked. And it was like 5 o'clock, and we're like, are we lost? because we should really be there by now. We're not that slow, are we? And he's like, I don't know, let's sit down and look at the map. So we're sitting down, we're looking at the map and kind of pondering where we might be if we've taken a wrong turn somewhere. We're pretty sure we hadn't. Ended up we hadn't. And then all of a sudden we see this guy and he's like just bebopping up the trail towards us, like literally at somewhere between a fast jog and a slow run, uphill towards us. And we're like, hey, dude, did you come from Tumbling Creek Campground? And he looks at us and goes, oh yeah, Mike, it's just down the trail there, about 20 minutes. You'll be there in no time. Sweet, okay? We're like, oh yeah, we're gonna get there in 20 minutes. We're gonna filter some water and cook some food, and we're gonna, it's gonna be so good. An hour later, we stumble into Tumbling Creek Campground, dehydrated, hangry, okay? And we are plotting how we're gonna find this guy, okay? Like that's how out of it we were. So we filter some water, get some food. And I look over at my buddy, who's also a physics teacher. This is the embarrassing part of the story. And I said, Sean, you know what we just did, right? He looks at me, shut up. We will never speak of this. So I'm breaking that. I speak of it every time because it's a funny story. I said, we let that guy, who, thinking back, was wearing like army fatigues and carrying probably an 85-pound heavy pack and was probably just out for a training run, okay? Tell us how long it took him, as an in-shape special forces guy probably, to run uphill 3 kilometers. Not 2 out-of-shape teachers on their summer vacation stumbling downhill dehydrated and hangry. We let him tell us how long it took him instead of telling us how far it was. Shut up! Yeah, so that's where it can get you into trouble. Like, there were a couple of times where we're like, that guy's full of crap. He had to have lied to us. He's messing with us, and we stopped and looked at the map again. We were ready to turn around. Like, that could have got us in real trouble. Okay? We'd have had to, find a place to camp where you're not supposed to camp just because we would have had to do something and there was no water. There were no fresh water sources around. We were in real trouble. Okay? So always make sure you get the answer you're looking for. Time is not usually the answer you're looking for in a situation like that. Okay? We use it simply because in our society and in European society, our modes of transportation are generally fairly reliable in terms of how consistently we can get from one point to another in a certain amount of time, right? When I asked you how far it is to Edmonton, you're like about 3 hours. It is. It's around that, okay? It's usually in that ballpark. Is it always exactly 3 hours? No, okay? But it's around that, and that's what people are generally looking for. Does that sort of make sense? Okay. Now, little review here of measurement, metric system. Okay? So in the metric system, the main unit, whatever it is, goes in the middle of this chart. Okay? Now, if I go down from the unit, okay, so this could be, we'll say like it could be meters, it could be liters, it could be grams. Okay, etc. Okay, if I go down one level from meters, okay, I would have decimeters. If I go down one level, right? How many decimeters are in 1 meter?
10.
Right. Okay. And if I go down one more level, what's the next level down?
Centimeters.
Right. Okay, how many centimeters in a meter?
100.
Okay. All right, what's the next one down?
Millimeters.
Right. How many there? 1,000. Okay, what are you noticing? Every time I go down a level, it gets how many times bigger?
10.
That's the metric system. Okay, the metric system is brilliant in its simplicity. Every level is a factor of 10 different than the level before. Okay, it's not like the imperial system where you have to remember there are 12 inches in a foot, 3 feet in a yard, 5,280 feet in a mile. Okay, there are 16 ounces in a pound. I can't even remember it all. You got to remember all the stupid numbers. Okay, that's why we've abandoned the imperial system in favor of the metric system. It works better. It's easier to use when you're going from converting units to another. Okay, now if I kept going down, okay, we used this next unit down, okay, okay? But it would be a bit of a jump. Would be micro, right? So this would be like 10 to the minus 6. Okay? Now, if we're going up the chart, what's the unit above the unit?
Deca.
Deca. Okay? And so, sorry, I drew this backwards. It doesn't matter. It's 10 times bigger. Okay? And then above that is
Hecta.
hecta, and then above that is kilo. Okay? Every step up is a factor of 10. Okay? So how many meters in a kilometer?
1,000.
How many grams in a kilogram?
1,000.
How many bytes in a kilobyte? 1,000. Okay? Kilo always means 1,000. Okay? Milli always means 1,000th. Okay? As long as we can remember those kind of rules, making metric conversions is really, really easy. Okay? We just have to remember kind of how that system works. But the beauty of it is it works no matter what we're measuring. Okay? I mean, it's meters, so it's length, it's volume, it's mass, it's memory space. It's all kinds of, but we use that for everything because it's just simpler to do it that way. Okay. Now, we said a minute ago that when you told me how long it took to get to Edmonton, that number wouldn't be accurate because it was dependent on 2 other numbers. So, those 2 other numbers were speed and distance. Okay, so this is one of the formulas we're going to look at today. And this formula. I'm not going crazy. Those are 2 different formulas.
What's with the weird, like, V on top?
That's an arrow.
Oh, that's an arrow? What?
Okay, so the little squiggly line that I put over top of the V and over top of the D, that's an arrow. Okay? When you have that over top of a symbol, it means that that is what kind of a quantity? Vector. It means it has magnitude, and because of that arrow, also has direction. Okay? So this formula is speed equals distance divided by time. And this one is velocity equals displacement divided by time. Okay? These formulas are on the back of your periodic table. Okay, so you have all these formulas, you don't have to memorize them. Okay? Okay, is a vector description of something always better than a scalar description?
Yes?
No, actually, but we get that idea, right? Because vector always seems better because it has magnitude and direction, okay? But there's times where that's appropriate and times where it's unnecessary, okay? So let's look at a couple examples here. So let's say I'm on this map here, okay? And let's say that I'm right here at Tumbling Creek. Or sorry, this is not Tumbling Creek, this is Seldom Inn. Seldom Inn Campground right here. Right outside of Seldom Inn Campground is a sign. And that sign says Snake Indian Falls Campground, which is this place right here. Okay, 32 kilometers. What has it told me? It has told me the distance from Seldom Inn Campground to Snake Indian Falls Campground. What is it assuming I'm going to do?
Get on the right path.
Right, it's assuming I'm going to follow the path. It has given me distance. Distance is a scalar quantity. Okay? When it tells me the distance, it means I'm going to follow this path to here. Do I travel a whole bunch of different directions along that path? I do. Okay? All it's telling me is this is how far you will have to go. Okay? That is the most appropriate way to tell me how far it is to Seldom Inn Campground. Or sorry, to Snake Indian Falls Campground. It would not have a sign outside of here that says that Snake Indian Falls Campground is 19 kilometers at 50 degrees west of north. Why would it not tell me that?
Because you can't go 19 kilometers west of north because there's no trails there.
Exactly. If I was to do that, I would be doing this. Okay? That's not giving me the distance, it's giving me the displacement. How far and in what direction? 19 kilometers, 50 degrees west of north. Okay? So when I get to Snake Indian Falls Campground, that will be my displacement. I will be 19 kilometers, 50 degrees west of north from where I started. To do that, I will have to walk 32 kilometers. Same trip, different points of view. Okay? We're talking about the same trip here, but those numbers are very different. Okay? Because they're looking at that same trip from a or through a different lens.
So is like one of them, like how long, like for a person to walk it, and then the other one's just like how far the actual two campgrounds are from each other?
In a straight line. Yeah, displacement is always your change in position. Okay, distance is how far you must go. Displacement is how much you displace yourself, right? How much do you change your place? Literally, displacement means change of place, right? So if my initial position is Seldom Inn Campground, my final position will be Snake Indian Falls Campground, and I will have changed my position in a straight line by 19 kilometers, 50 degrees west of north. Okay, does that make sense? Okay, so this is that thing I was telling you about yesterday when I jokingly said, okay, Darth Vader betrayed and murdered your father, Darth Vader is your father. Okay, it's the same story, but it's from two different points of view. They're both true. Okay, in this case, they're also both true. Okay, in order to get to that position, I will have to walk a distance of 32 kilometers. Okay, why does the sign not say that? Because it's not appropriate to tell me, hey, walk on this line, silly. Okay, like this would be all bad. With no trail, every one of these rivers is basically a canyon, okay, with no bridge. This is a glacier, this gray stuff. Okay, it's not really smart to walk on a glacier in the summertime. You could fall into a crevasse, okay, and die. That would be bad. Okay, so yeah, I wouldn't go that way. Now, what if I'm a helicopter pilot? Do I want the vector or the scalar? I want the vector one, because I can fly in a straight line. I don't have to worry about the trail. Okay, I'm just going to go straight across. Okay, so if you're looking to go into like careers that involve like navigation, so that could be an airplane pilot or navigator, okay, or anything on the open sea, okay, so like a cruise ship navigator or something like that. Vectors are a big part of those because you have to take into account all these things that you can actually travel in more of a straight line. Okay. All right. So does that make sense? Difference between vector and scalar? Okay, so if someone asks you, how far is it to the zoo? Okay, you might say that it is, okay, like so you call it up on Google because that's what we do these days. Okay, call it up on Google Maps, and it would tell me that it's 42.8 kilometers. Is that distance or displacement? That's the distance, right? That line there, that blue line that is the path I could follow, goes in different directions. It is not a straight line. Okay, I would have to drive my car 42.8 kilometers, okay, and I would get there in, it says, 30 minutes. Okay, is Google usually fairly accurate on its time estimations?
Yeah.
Why?
Because it knows where there's
exactly. It actually, this is gonna sound creepy, and it is a little bit, okay? But every time you drive by one of those signs that tells you how long it'll be to the airport or to like, you know, Deerfoot Trail or whatever, those signs are pulling geotags from your phone, Bluetooth, okay? They're pulling your position, okay? Now, if you've agreed to share it, right? You have to have your location sharing, stuff like that on it. Okay, it'll pull it, and what it's doing is it's following, and the next time you drive by one of those signs, it's got, okay, that tag came from that, now it's here, it took that person this long, okay? And it feeds that all into the data to help it with its calculations, okay? It knows how fast, okay? Like I just noticed this the other day because I was driving my wife's car, which has like the whole new CarPlay thing in it, okay? And it actually came up and was like, there is an accident on your route. Do you want to reroute? And I'm like, no, I'm too close to it now. I can't miss it. So I'm stuck in this thing. And then as I'm getting closer to it, I can see that the tow truck has just pulled the accident away. So now it's clear. So, and then it pops up on the screens like, is the accident still there? And so I'm like, hey, read, click that, say no. Like, so it's asking you to update it, and so it's giving updates all the time. Okay? So it knows how fast people are going on average through the sections of road that you're going to travel. So its time estimate is usually pretty accurate because it's actually using the average speeds of other people following those same routes. Okay? So when it tells you it's 30 minutes, it's probably a pretty good estimate. Okay? Unless something were to happen in the middle. Okay? Then it'll reroute you and it'll change your estimated time. Okay, so it's going to give you distance, it's going to give you time, and it's using speed. All of those are what kind of quantities? They're all scalar, right? None of them have a direction. They're all scalar quantities. Anybody, well, you guys haven't probably been driving long enough, I hope. When you get a ticket, is it a speeding ticket or a velocitying ticket? Right, okay? If you get pulled over and the police officer asks you how fast you were going, please give them your speed. Okay? Because if they walk up and say, you know how fast you were going, okay, and you say, yes, officer, 130 kilometers per hour at 10 degrees south of east, there will be follow-up questions. Okay, usually involving whether you've had anything to drink today. Okay, perhaps some field sobriety tests in your future, because that's not the way they expect that answer to come. Okay, they asked you how fast. How fast is speed? Now, if he asked you how fast and in what direction, then it would be appropriate to tell him which direction you were going. But if they're asking you which direction you were going, it probably means you were going the wrong way in addition to too fast, and you're already in so much trouble. Okay, so just keep that in mind. There are times where scalar is appropriate. That would be one of them, okay? And where vector is appropriate, okay? Usually in trackless environments or any situations where you can actually travel in a straight line from A to B, vector is better, okay? If you're talking about following a system of roads or tracks, scalar is probably better in those situations, okay? That makes some sense? All right. I keep forgetting to change that. Your notes should say a more descriptive description, right? I keep forgetting to change it on here. Okay, so what's more accurate, vector or scalar? The answer is actually it depends. We get this impression, though, that because a vector quantity gives me extra information, that it's more accurate. Accuracy doesn't depend on how much information I give you. Accuracy depends on how I measure something. Okay? So let's say I take you guys out back to the track, and I say, and I give one of you a normal meter stick. Okay? It's got all the stuff on it. And I say, measure the track. We go all the way around the track with this thing. Okay? It's measured to the nearest millimeter. So when you get all the way around, okay, you're going to be able to tell me that the track is 400.000 meters. To the nearest millimeter. Okay? You'll be accurate to plus or minus 0.001 meters. Because that's the stick I gave you. Now, the other group I give a stick. It's a meter long, but it has no markings on it. But I can tell you that it is 100% accurately 1 meter long. When that group gets done, they can tell me the track is 400 meters. Because their meter stick doesn't have any markings on it, they can only be certain to plus or minus 1 meter. Okay? Which one's more accurate?
Top one.
The top one. Accuracy doesn't depend on whether it's scalar or vector. It depends on how it was measured. Accuracy comes from measurement. Okay, it doesn't come from whether it's scalar or vector. Okay, question?
How do you know this specifically? Have you done this before? Have you like just?
A running track is always 400 meters.
Oh,
Yeah. And I coached track for 25 years.
My dad goes track. My dad goes track.
So, yeah. Okay, that sort of makes sense, what the difference between accuracy and measurement? Okay, so accuracy comes from measurement. How you measure something determines how accurate it can be. Okay. All right, let's talk about this trip as an example here. So let's say I'm going to go from my house to Walmart. Okay, since I don't live right next to Walmart, I can't walk in a straight line to Walmart because there's like houses and rivers and stuff in the way. Okay, so I'm just gonna follow a path. Okay, go from my house and follow the path and go across the river and eventually get to Walmart. All right, so when I have walked all that way and I've been tracking myself on my phone, it tells me that I have walked 4 kilometers. Okay. I left my house at 1 p.m. I arrived at Walmart at 1:30 p.m. So it took me exactly how long? 30 minutes, or 1/2 of an hour. Okay. Okay, how fast did I walk?
8 kilometers.
8 kilometers an hour. Okay, how did I do that? Or how did Kessler do that? Okay, V equals D over T. 4 divided by 0.5. Okay, so this is in hours. This is in kilometers. What's kilometers divided by hours? Kilometers per hour, right? They can't cancel each other out, so we just put them together. Okay, so my speed was 8.0 kilometers per hour. Okay, everybody all right with that? All right. Now, what does that line represent? That represents my displacement. It will be my change in position from my house to Walmart. Okay? Let's just say that I figure that to be, I have the numbers on the next page. I think I do actually. I think I actually figured it out. 2.8. Okay, so it's 2.8 kilometers, but I also have to give a direction. So here's my compass. So this is north, east, south, and west. Okay, so this line here would be due east. I'm a bit south of that. I'm just going to say it's 38 degrees south of east. Okay, that's my displacement. Is my time still the same?
Yes.
Yeah, we're talking about the same trip here. Okay, it took me a half an hour to walk 4 kilometers. It also took me a half an hour to change my position by 2.8 kilometers at 38 degrees south of east. Okay, both of those things take the same amount of time for me to do. Okay, so the time is still 0.5 hours. So what's my velocity? Do I calculate velocity in a similar way? Do we do this? Velocity equals displacement divided by time? Okay. So when I go velocity equals, okay, displacement divided by time, that's going to be 2.8 kilometers at 38 degrees south of east divided by 0.5 hours. Okay, so what I'm going to get is that my velocity is 5.6, if my mental math is right, kilometers per hour at 38 degrees south of east. Okay? I can only go 38 degrees south of east by walking 38 degrees south of east. Would you agree? Like on average? Okay? Your displacement, your total displacement, and your average velocity are always going to have the same vector because one comes from the other. Okay? Does that sort of make sense? Right? I couldn't have walked north for a half an hour and ended up at Walmart. Okay? That wouldn't work. All right, everybody follow that part. Okay, so that's the same as the seldom in to Snake Indian Falls campground example. Okay, except this one's got real numbers. Okay, so same trip, looks different, numbers look different, but it's the same trip. Here's where it gets weird. Well, you may not find this part hard to believe. I get to Walmart and I realize I don't have my wallet or my phone. So I can't buy anything. I'm not gonna walk around Walmart for the fun of it. Okay, so I just turn around and I go home. And I follow exactly the same path. When I get home, it is 2 o'clock. And since I followed the same path, I have walked how far?
8 kilometers.
Okay, so is my average speed still 8 kilometers per hour? It is. Okay, because I've gone there and back and I followed the same path and I obviously walked at the same speed if it took me a half an hour to get home. Okay, so for the whole trip, okay, I still do the same thing. V is still d over t. It's just now it's 8 kilometers divided by 1 hour. Okay, so I still get 8.0 kilometers per hour. Okay, now, vector perspective. When I get home, what's my displacement?
0.
Right. Okay, displacement is your change in position. We actually calculate it by going final position minus initial position. Well, my final position is home, and so was my initial position. If the final and initial are the same place, I didn't change my position at all, did I?
No.
Okay, so then my total displacement is 0 kilometers over 1 hour. So what's my average velocity over the whole trip?
0.
0. I don't even have to put units on it. Okay, you can't put units on nothing. Okay, so I did all of this, and from a vector perspective, accomplished absolutely nothing. Okay, that make sense? Okay, application question. In your car, there's a little meter that tells you, it's called your odometer. What does it tell you?
How far you've gone.
Right, how far you have driven the car. Distance or displacement?
Distance.
Right. Why would displacement be utterly useless for that meter?
Because it would just keep measuring from where it started.
Right? So every time you come home, it'll read? No, it'll read how far it is from the dealership you bought it at to your house. Every time you take it for an oil change, it'll read 0. It's a trick question. Okay? But yeah, you try now, like 10 years later, after you've driven that car all over the place, if that thing reads displacement, leave it in your driveway. Tell people to come to you. Look, this car has 3 kilometers on it. And that's a way to rip people off, right? That's exactly why it doesn't work that way. Okay? If people want to look at that thing and go, yeah, you drove that car 250,000 kilometers? That's a lot. I don't know if I want to have that car. It's got a lot of kilometers on it. Okay? So they might be a little, more leery about it. Back in the day, when we didn't have it all digital, people would like pull the face off of their dash and roll the odometer back with a pin, okay, to rip people off. They'd take a car that had like 500,000 kilometers and go tick, tick, and it would roll. They'd roll it back to like 100. Okay, you can't do that now with the computerized cars because it's all digital, and the computer knows how far you've driven it unless you know how to reprogram the software. Okay, which I'm sure people do. Because there's always a way to rip people off. So. Okay, does that sort of make sense? Okay. So that's the difference there, that difference of perspective between vector and scalar. Okay, it's the same trip, but it looks very different depending on your point of view. Okay, so like we said, distance is how far the object has traveled regardless of what direction it went. It's just how far it was from A to B. Okay, displacement is the change in position, straight line between A and B. Okay, so just make sure we understand that those two things are different. Speed and velocity have the same relationship. Okay, speed is how fast you go. How many kilometers in an hour will you travel, regardless of direction. Okay, velocity is how fast did you change your position with direction. Okay, so if we back up again to this picture, speed was bigger than velocity when we were just walking from the house to Walmart. Agreed? Okay, does that make sense that it should be? Yeah, it was a bigger distance, right? Distance will always be bigger than, or in some cases equal to, displacement, but it'll never be smaller. Why?
Because displacement is the total distance from A to B in a perfectly straight line, and you can't get it any closer using distance.
Right. The shortest route between 2 points is a straight line. That's displacement. Displacement and distance can be equal if you actually traveled in a straight line. But distance will never be smaller than displacement. Okay? Everyone all right with that? Same with velocity and speed. Okay, so speed and velocity have a similar relationship. Okay, we talked about this. Okay, it was 8 kilometers per hour to walk there. Okay, but it was 5 kilometers per hour at 38 degrees. Well, I put north of west on there, but it's south of east on the map. Okay, because of the direction we had to go. Okay, yes, displacement is shorter, so it seems like we're walking slower. We're not. It's just a matter of perspective. Alex. All right, everybody okay with that so far? All right, I'm gonna give you about a 5-minute break here in the classroom and then we'll carry on with some more stuff here. Okay, we gotta review a little algebra here. Okay, so you gotta think back to the mole equation. Okay? No triangles. Okay, no triangles. You don't need triangles. So we are not going to use triangles because in this unit we are going to use a whole bunch of formulas that cannot be solved with the stupid triangle. Okay, so formula sets up like this, whether it's speed, velocity, displacement, distance, I mean the manipulation, the algebra is the same. Okay, what were our 3 rules of algebra? Anybody remember?
Whatever you do to one side, you do to the other.
Okay, that's the second rule, the golden rule of algebra. What you do to one side, you do to the other. What's the first rule? You want to move something? Do the opposite. That's rule number 1. Okay, and okay, the third rule, move what's not attached first. Okay, we don't need that for this one. Okay, but we will when we get into our 4 variable formulas. All right, so let's say right now I want to solve for D. Okay, how do I manipulate this formula to solve for D?
Times both sides by t.
Right, I've got to move t over to the other side. Right now, I'm dividing by t. The opposite of divide is multiply. Okay, so I am simply going to move t over here. T times v. That's exactly what we did with the mole equation when we were looking for mass. We would move molar mass over to the other side by multiplying. Okay. What if I want to solve for t?
Move D by.
Well, if I multiply both sides by d, I'll have d squared.
Divide.
Okay? I need to multiply t first. Here's why. Okay? Because I know the gut instinct is, well, I got to move d. I got to get t by itself. But if I move d over to this side by dividing it, what do I get when I go d? Oh, that's not what I wanted. I asked for green. What's d divided by d?
1.
Right, 1. So when I do that, I don't get rid of the d's. Okay? Is 1 over t the same as t?
Yeah.
Okay, let me ask that a different way. Is 1 over 2 the same as 2?
No.
Then 1 over t is not the same as t. Okay? Just so we're clear, it's okay. We sometimes have to think that one through. Okay? All right, so this doesn't solve for t. This doesn't help me, does it? No, it solves for 1 over t. That's not what I'm looking for. Okay, so what I want to do first is actually move t. I don't want to solve for something that's on the bottom of an equation. I want to move it to the top. Okay, the best way to move t to the top is to move it over here. Okay, now you're probably going, Coderre, that doesn't isolate t yet. What do I do with v now? Right. Now I just divide both sides by v. Now t is isolated. Am I going to get t? Am I going to get the right units?
Yes.
Well, let's check. Okay, let's say that d was in meters and v was in meters per second. Okay, when I divide meters by meters per second, what happens to the meters? They cancel, and I'm left with? Okay, that seems to work then. Okay, you can always check your algebra by plugging the units in. If you get the right units, then you know you did the right algebra. Okay, everyone all right with that manipulation? That's the extent of the manipulation for v equals d over t. If you're solving for v, you'd have to do nothing. Okay, if you're solving for d, you move t. All right, if you're solving for t, you move t and then move v. It's not rocket science. Okay, as long as we can follow those rules of algebra, we're good. Okay, everyone all right with that? Okay. All right, so those 3 rules, just in case you don't have them, might not be a bad idea to write those down. Yeah, I'll give you a couple minutes for that, and then we'll look at a few example problems like you might see on Friday. All right, let's just go through a few examples here, simple examples, okay, and kind of see where I would give marks on a question like this. So copy this one down here real quick. How far will a deer running at 15 meters per second travel in 45 seconds? Okay, so writing down our givens is still our first step here. But we have to be a bit more careful writing down givens in physics than we did in chemistry, because there's no vector and scalar stuff in chemistry. Okay, so when it asks how far, what does it want?
Distance.
It wants distance. How do I know it doesn't want displacement?
It doesn't say from like the starting point.
And it also doesn't ask how far and
What direction?
in what direction. It just says how far. How far is distance? Okay, so I know this question wants me to calculate d. Okay, then it says running at 15 meters per second. What did they give me?
Speed.
Speed. How do I know it wasn't velocity?
They didn't give you direction.
They didn't give me a direction. Okay. Okay, in 45 seconds, what did they give me there? Time. Okay, so you'd get a mark for your givens. Okay, and you'd also get a mark for choosing the correct formula to use. I know right now that seems silly because there's only one formula, but later on in the unit when there's like 24 formulas, okay, you'll get the idea why that's worth a mark. Okay, so I get a mark for this. Now, I've got to solve for d, so do I have to do some algebra?
Yeah.
What do I have to do with t? Yeah, I got to multiply it over to this side. Okay, so t times v equals d. All right, let's just do a quick unit check here and make sure that that's going to work. This is going to be seconds times meters per second. Okay, what's going to happen to the seconds? They're going to cancel. I'm going to be left with meters. Okay, my manipulation's okay? Okay. All right, so let's plug in our numbers here then. Time was 45 seconds. Okay, and it's going to do that at 15 meters per second. Okay, so 45 times 15. Okay, 675 meters. You are fast. Okay, 15 meters per second is really fast to run for 45 seconds. Okay, like the world record for the 400 meter, okay, is around 40, what is it now? It's 40 point something seconds. Okay, so a really, really, really fast human could only run about 415, 420 meters in that same amount of time. Okay, because they would run slower. Okay, everybody all right with that? So you get a mark for your givens, you get a mark for your formula, a mark for your algebra, a mark for your answer. Okay, everybody all right with that one? Okay. Okay, I'll give you a minute, write that one down. See if you can solve it, and then we'll walk through it together. Okay. How long? What am I looking for? Time. Okay. Okay. Will it take a tortoise to crawl 200 meters? What did they give me there?
Distance.
Okay. How do I know its distance?
Because the
No direction. Okay, at a speed of 25.25 meters per second. Well, that one's pretty easy because they outright say it's speed. 0.25 meters per second. All right, so I've got D, I've got V, and I'm looking for T. All right, so 1 mark for our givens and 1 mark for identifying. We'll have to use this formula to calculate that. Okay, now I'm trying to solve for T, so I'm going to have to move T over to this side by multiplying both sides by it. And then I'm going to have to divide both sides by V. So I'll be left with T equals D divided by V. So that'll be 200 meters divided by 0.25 meters per second. Are my meters going to cancel? Yeah, I'll be left with seconds. Okay, so 200 divided by 0.25 should be 800 seconds, yeah? Okay, so hopefully there's no one chasing it or trying to beat it. Okay, because that's a lot slower than the deer. Okay. All right, everybody okay with those? Okay, guys, like we get into more complex formulas, the algebra becomes a little bit more involved, but the rules are always the same. Okay, so I know a lot of people are like, oh, I'm not good at math, so I won't be good at physics. Not true. This guy's not good at math. Okay, and I'm pretty good at physics. I don't mean to brag, but I'm pretty good at it. Okay, you don't have to be good at math to be good at physics. You really don't. In fact, some of my strongest physics students were not strong math students. Yeah. Okay, I want you to write this one down. This is a vector problem, but it's also got a couple of steps. So I want to walk you through one of these. Okay, so I'm going to have you copy that one down. Okay, don't start it. We'll go through it together. Okay, so this question adds the word average before velocity. Okay, so the first thing we have to talk about is both of these formulas, speed is distance over time, and velocity is displacement divided by time, actually mean this. It's not written on there, but they actually mean this. Average speed is total distance divided by total time. And average velocity is total displacement divided by total time. Okay? When we're just doing a one-step problem like the first two we did there, our total was the only number we got. Okay? But by default, these formulas mean average velocity is total displacement divided by total time. That can be done section by section on a trip or looking at the whole trip together. Okay? So, on a question like this, when we write out our givens, we have to recognize that in this trip, this trip has two different parts. Okay? There's a part where the bus travels north, and there's a part where the bus travels south. Okay, so what I want to do is break the trip up and write out my givens for each part. Okay, so I'm just going to say part 1. In part 1, the bus travels 100 kilometers north. What did they give me there?
Direction.
Direction.
Displacement, right. Okay, 100 kilometers, and then I just put n in brackets, that's north. In 1.2 hours, what did they give me there?
Time.
Time. Okay, that's all I'm given for part 1. In part 2, it tells me it travels 62 kilometers south. What did they give me? Displacement. In 0.9 hours, so another time. What's the average velocity of the bus? Okay, so that means over the whole trip. Agreed? All right, so according to this formula, to get the average velocity, I need the total distance, or the total displacement, and the total time. Can I get that from my givens? I can. All right, so here's where vector comes into play. Okay, so I'm just going to make another kind of thing here that's called totals. Okay, the bus goes 100 kilometers north, and then it reverses and drives 62 kilometers south. From its starting position, what's its displacement? 38 kilometers north. Okay, it went 100 north and then 62 south. It is now 38 kilometers north of where it started because it essentially did this, right? This would be 100 kilometers, and then, didn't mean for that to scroll back down. Okay, and then it did this. And I didn't get the purple line I wanted anyway. Okay, that would leave me with 38 kilometers from my initial position to my final position. Okay, everyone all right with that little bit there?
So the total distance is the part 1 minus part 2?
No, the total displacement
Oh,
is.
sorry.
The total distance here is 162 kilometers.
That's what I meant.
Okay, so the total displacement here, okay, we just figured out, is 38 kilometers north. What's the total time? 2.1 hours. Why didn't I subtracted the displacements? Why didn't I subtract the time? Okay, I didn't go back in time. Okay, time kept going forward. Okay, you never ever subtract time. Okay, well, when you're doing something like this. Our total time is going to be 2.1 hours. Total always means add. Okay, what we really did here was add as well, right? We would have had positive 100 plus negative 62, right? All right, so now I've got my total displacement, I've got my total time, now I can calculate my average velocity. So I'll have 38 kilometers north divided by 2.1 hours. Okay, so 38 divided by 2.1. So we'll say 18.1 kilometers per hour north. Would you lose the mark if you didn't put the north on?
Yes.
Yes, because then you give me a speed. Okay. Everybody all right with that? What's the average speed of this car? Or this bus? Can I calculate that?
Mm-hmm.
Okay, what was my total distance?
162.
162 kilometers. What's my total time?
2.1.
2.1 hours. Okay. Okay, total distance divided by total time, 77 kilometers per hour. Okay, why such a much higher number?
Well, because it's the total, whereas displacement, you're actually kind of subtracting your distance.
Right, I reversed, and because displacement is vector, that makes the number smaller. Okay, the total displacement then is a lot smaller because I reversed direction. Okay, scalar, when you reverse direction, scalar quantities get a lot bigger than vector quantities because you're having to keep direction in mind for the vector quantities. All right. Okay, very similar question, except instead of a bus, it's a rabbit. Okay, give that one a try on your own, see how we do. Okay, just in case you're a little bit stuck, I'm going to put out the givens here, okay? Okay, so the big trick here, guys, because they tell you they're running west, both the 17 and the 32 are both vector quantities. The 32 is 32 meters west, okay, because they indicate in the sentence that both of these quantities are west. Okay? Okay, just for the sake of getting through this before the bell goes here, guys. If I want to get average speed, I need total distance and I need total time. Okay, and if I want average velocity, I need total displacement and total time. Okay, do I have the displacement for part one? No. Can I get it?
Yes.
Yes. Okay, I just have to do a v equals d over t calculation, right? So I've got to go that v equals d over t and then multiply both sides by t. Okay, so 22 times 12 will tell me what the displacement in part one is. 22 times 12 is 264 meters east. Okay, I don't have time in part two, but I need it. Can I get it?
Yes.
Yes, same thing. Just going to manipulate v equals d over t for t this time. Okay, so I'm going to take that 32 divided by 17. Okay, so we're looking at 1.88 seconds. Okay, so now that I've got D and T for both, now I can do my totals. Agreed? Okay, so let's do the average speed first. Am I worried about the directions for speed? Okay, so if I want to make both of these distances, I just forget that there's an east and a west attached to them. Okay, so 264 plus 32, okay, 296? Is that right? Mental math kind of fast. Okay, and then 12 plus 1.88 is 13.88 seconds. Okay, so my average speed is just those two numbers divided by each other. Okay, so 296 divided by 13.88. All right, so the average speed is 21.3 meters per second. What am I going to do differently for the velocity? Right, now the direction matters. I'm not going to add them, I'm going to subtract. Or I'm going to add and one of them is going to be negative because it's in the opposite direction. Okay, so I'm going to take the 264 and subtract the 32. So that's going to give me now 232 meters east, because the east was the bigger of the two, divided by the same time, still 13.88 seconds. Whoop. 32 divided by 13.88. Okay, so my answer there should be 16.7 meters per second east. Okay, is that terribly difficult? Not really. You're not gonna get anything harder than that on Friday.
Oh.
Okay, that's as tricky. That's what we're gonna work on tomorrow. Okay, whole class tomorrow, we're gonna work on B equals B over T problems of ever increasing complexity. Okay, good job today, guys.